And vertical stretch, respectively compression of radical function. First, let's analyze the reflection of radical function over x-axis. Reflection over x-axis is if f of x is equal to the square root of x, so is a parent function, is given by minus f of x is equal with minus square root of x. In this case, we're going to have a reflection over x-axis. For example, we see one example here down, which a parent function, the graph of the parent function is with a red curve, f of x is equal to square root of x. And if we have a function g of x, which is a minus square root of x, this function is a reflection of parent function over x-axis. So the points in the x-axis are going to be the same, but the only difference, what is going to be in the graph, all the points that lies in the graph f of x are going to be different from all the points that lie in g of x. But the points that lie in these two graphs are going to be the same. If we want to see a little bit in the table how it looks, we can see from that perspective too. For example, we already know this is a very known from the previous videos, the parent function f of x square root of x. So those are the results that we get. But if we have g of x is equal minus square root of x, as we see here, the coordinates of the points in the x-axis are the same. Same are here, and same are in the g of x. But the only difference is the points are changing in the y coordinates. For example, here I have 1, 2, and 3, and here we have minus 1, minus 2, and minus 3. The only point is in the origin is the same. Then we have a reflection of radical function over y-axis. If the reflection over y-axis is if we have a f of x is equal to the square root of x is given by f of minus x. So the minus x is the radicand is a negative here. The variable is negative. In these cases is going to be the reflection over y-axis. What's happening here, as we see, the y coordinate is going to be the same for both functions, but the x-axis are going to be different. Here, for example, here is 1 minus 1, here is going to be 1. Or if here is let's say 5, here is 5, here is going to be minus 5. But the y-axis are going to be the same. For example, 1 point here, if I'm going horizontally this way, is going to be the same point here. So the y-axis are going to be the same. And if we want to look from the perspective of the tables, we can see this way. So as I said before, y-axis are the same. The y-coordinate of the points is the same, is here, and same is in the blue function. But the only difference is in the x-axis, the point in the x-coordinate. See here we have 1, 4, 9, and in the blue function is a negative 1, negative 4, negative 9. For instance, if I put a negative 1 in a negative x, I'm going to get 1. But here, for example, 1, if I'm plugging instead of the x, I'm going to get 1. So the only difference here, what is going to this function, is the difference is going in the x coordinate of every point, which is going to be in one is negative and in the other are positive. Now let's see vertical stretch and compression of radicals. As we talked about before, the general form of square root functions is f of x is equal with a square root of b times x minus h plus k. But today we are looking at this factor a. This factor a is a factor that indicates the vertical stretching or compression factor. If absolute value of a is greater than 1, then we have a vertical stretch. If the absolute value of a is smaller than 1, we have a vertical compression. Let's say here is the parent function, and we are talking here with reference to the parent function, f of x is square root of x. And here is the factor a is a greater than 1, so we have a vertical stretch. And parent function is going to stretch vertically. And all the points here in the y-axis are going to be bigger. But what's happening with the x-axis are going to be the same. And now the green function here, the factor is smaller than 1, so it's 1.5. And here we have a compression. And all the points in the y-axis are going to change, but in the x-axis is going to be in the three function are going to be the same. But the only difference that is going to happen in the points in the y-coordinate. And if we want this to see a little bit from the perspective of the tables, we can see down. For example, here is a parent function f of x. And when we have a vertical stretch, is a factor 3 is greater than 1. And as we see here, every point in the y-coordinate is going to multiply by 3. 3 times 1 is 3. Here is 3 times 2. This 3 times 2 is 6. And here is a 3. 3 times 3 is 9. So every point in the y-axis is going to be larger than the values of the y-axis in the parent function. And if we are looking over the green function, 1 over 2 is smaller than 1, and because of that we are going to have a vertical compression. So all the points here that are in the y coordinate are going to multiply by the factor 1.5. And when we multiply by the factor 1.5, each point is going to be smaller. And for example, 1.5 times 1 is 0.5, 1.5 times 2 is 1, and 1.5 times 3 is 1.5. The same thing is going to happen when we have, for example, in a negative, in the front if it's negative sign. And as we saw a little bit early in the video, f of x is equal to minus square root of x is a reflection over x-axis of the parent function. The parent function was f of x is equal to square root of x. But now we are looking with a reference to this function here, what's going to happen with the function h of x and g of x. And because the factor here in this function, green function, is a greater than, if the absolute value of minus 2 is a greater than 1, it means we have a vertical stretch. So here we have vertical stretch. And as we see, every point here is larger than this point here. Now, if we are looking, for example, the factor here, minus 1.5, and if we are taking the absolute value, 1.5, negative 1.5 is going to be smaller than 1. And because of that, and we are looking from the perspective of the function f of x minus square root of x, this function is going to be compressed, going to be smaller. This is going to be here, and this space difference is going to be much smaller from here to here than from here to here. So that's why we have compression. And if we look, for example, the green function here, the space from here to the x-axis is bigger than the space from here to here. Therefore, here is happening stretch, vertical stretch, to look from the perspective, visual perspective. And now let's see from the tables how it's happening in the tables. For example, if this is a minus f of x, and as we see, every value here, we are talking in absolute value, is greater than minus 1. For example, absolute value of minus 2 is greater than absolute value of minus 1. And here, for example, absolute value minus 4 is greater than absolute value minus 2. Or those differences in the terms of the space are the greater space is going to create. Same thing happening here. And if you look, for example, in the vertical compression or shrink, if we are talking here in the terms of the absolute values, and how is it going to be created the space between the x-axis and the graph, here is going to be smaller space between this graph and x-axis than it's from the f of x of square root of minus square root of x. And as we see here, we see already in terms of the spaces, because if we are talking in terms of the numbers, normally it's a little bit confusing, because the numbers minus 3, for example, or let me go a little bit further. If we talk in the terms of the number, we already know minus 4 is smaller than minus 2. But the space, how it creates and how it looks in the graph, so this space is a greater, and it means is what is happening in the graph is happening in the stretch of the graph, and here is compression of the graph.